Hello, everyone. You are now tuned in to Retrotec webinar, The Impact of Wind on Building Airtightness Tests. And we have special guests with us here, Valerie Leprince, tuning in all the way from France. And so there's a lot of research that's being done in airtightness in buildings, and Valerie's got her hands in a lot of that going on, especially in Europe, and a lot of that's still having an impact here with us in the States. And so we're really happy to have her come on. If you've seen some of the videos that we've put out lately, I'm sure you can tell we've been talking about wind and blower door tests quite a bit lately, and we figured, let's see if we can get one of the best experts out there to come talk about it with us. So we're really appreciative to have Valerie come on and talk with us, especially on her first day back from vacation. So we really appreciate that. So
I'm glad to be here.
Yeah, so thank you. And so with us too, we have Lee Canigali. If you've ever called in for tech support at Retrotec before, then you've spoken with Lee. And of course, Ben Walker, one of our co-CEOs that's basically in charge of all things technical at Retrotec. So thank you guys for joining us as well. So we will be giving one BPI CEU with this webinar. So if you want that CEU, go ahead and use the Q&A box and enter your name, your email address, and your number, and we'll get that input for you. And so Valerie has broken up her presentation into 3 different sections, and so we're going to take questions at the end of each section. And we're really excited about this. We were just talking earlier. This is going to be one of the more technical webinars that we've had in quite a while. Valerie's done some great research on airtightness testing and how that impacts buildings and the equipment as you do a test. So we're really going to get into the weeds today, and it's going to be great. So if you have questions about it, now is your time to ask. And without further ado, I will turn it over to Valerie.
Okay, thank you. So yeah, I will make a presentation about the impact of wind on building airtightness test. So first of all, I will present myself because, well, I think most of you do not know me. So I'm French. I have been working for the French Ministry for Construction 10 years ago. I was involved in the energy performance regulations that has imposed mandatory tests for every new building, new residential building in France since 2013. And I was also involved in the French standard dealing with the building airtightness test protocol. Since 2012 now, I'm an independent consultant on ventilation and airtightness, and well, 1/3 of my work is dedicated really to standardization activities on the ventilation, and I'm the convener of the working group dealing with the inspection of ventilation system. And another 1/3 of my activity is to be a consultant for INIV, AIVC. So you may not be familiar with the Air Infiltration and Ventilation Center. It's an international group dealing with air tightness and ventilation and setting up conference every year. Well, every not COVID years. And in this context, I am the pilot of a working group called the Tidevent Airtightness Association Committee that gather airtightness tester, researcher, and also people from the industry from Tidevent. So if you need some more information, I have put some link. And since 2017, I have also been a convener of a working group about the impact of wind on airtightness test, and I will talk to you about a bit more about that later. So I'm a consultant for HINIV, and HINIV has set up a platform called Tidevent Europe that gather group leading partner from the industry in partner in the building ductwork airtightness solution and testing. They are gathered together to help raise awareness and foster new development in policy, research, and recommendation on airtightness. So the objective of this platform is really dissemination. We do webinar, we co-organize the AIVC conference, and we publish paper to try to really help disseminate information on building and ductwork airtightness. And one of the actions for me as a consultant for Tidevent has been to lead the working group about the impact of wind on airtightness test. This is an AIVC project, and the objective was to better understand the uncertainty due to wind on airtightness test and to improve the test method, to propose things to improve the standards. So output, it's not finished yet. It's still an ongoing project, and we still have meeting to do with this working group, is to have an information paper published by the AIVC. So if you are not familiar with ventilation information paper, you can go to this link also. It's free of charge. You can download everything that you would like on this. There is a lot of very interesting stuff on the AIVC airbase. And we also will organize a tight vent webinar on this subject, so you can have a link have a view also of tight vent webinar with this link, and we will probably organize it by the beginning of 2021. So you may ask yourself, who is interested in the impact of wind on building air tightness test? In fact, a lot of people are. So you see here all the participants to the working group, and there are PhD students like Adeline, Martin, Frederick, and also Xiaofeng in Nottingham as 3 PhD students. So we have participants from a bit everywhere, researchers that really want to improve the knowledge on the impact of wind on air tightness test. But one thing I have to say at the beginning, this presentation partly includes information discussed in the group, but I'm the sole responsible for its content, and it has not been reviewed neither by the group nor by tight vent or INIF. So please do not call one of those people saying what the French girl says rubbish, it's your fault, you co-signed it. It's not their fault, it's just my own responsibility here. And discussion, as I say, this working group is still ongoing, so the conclusions may change by the time we publish the last paper. So again, it's really open to discussions, and I will be glad to discuss it with you. So one question is, why do we care that much about wind, about the impact of wind on air tightness test? What is important to know is that in Europe, we have more and more airtight countries that impose air tightness tests to be performed for every new building with the required target value. And when you have a low required target value by the law, you need to perform reliable tests. And you need to have not too many limitations on allowable test conditions for a lot of tests to be performed. The problem is with the air tightness test, we have multiple sources of uncertainty. We have the measurement device itself, its accuracy and precision. So we try to solve this problem with calibration. We have calculation assumptions, the regression analysis, the model, and this is much more difficult to solve. We have got the tester behavior. We try to solve it by training and setting up competent tester schemes. In most countries where we have a minimum requirement on air tightness, we have also the tester need to be qualified by a competent tester scheme. And there is something on which we cannot do anything, which is wind and stack effect, and it's not properly addressed in ISO. All those sources of uncertainty are not properly addressed in the ISO 9972, and we really do need to work on it to improve the protocol and limit the impact of wind and stack effect. Another problem, at least in some regions, is allowable test conditions. According to the standards, the zero flow pressure shall not exceed 5 Pascal for the test to be valid. And it can be a huge problem when you live, for example, in this part of France, in Brittany, or in western part of Ireland. It's very windy regions, and sometimes the tester has to come 2 or 3 days in a row before he can find a day where he can perform the test. And this is a big constraint for him. And so we are also trying maybe to say, okay, maybe in some cases we can adjust the protocol not to need to the maximum of 5 Pascal. So as Thomas said, I will divide the presentation in 3 parts. The physics first. So I have put an equation, but don't worry, I don't put that much equation afterward. Then a literature review, and at the end, how to limit the impact of wind on the air tightness test. And we will make a little break between each for questions. So regarding the physics, what is important to remember is that the wind has an impact on the result of the air tightness test despite the zero flow pressure subtraction. The zero flow pressure subtraction is not the solution to avoid the impact of wind. There is at least 4 issues with wind. I'm sure we can find some other, but those are the most obvious, I would say. This is the wind variations between before, after the test, and during the test. The impact of wind on the external pressure sensor, the uncertainty due to wind fluctuations, and the model error. So I will just give some explanation about the wind variation. What our ISO standard said, and I guess it's probably the same in the ASTM, is that we record the zero flow pressure before and after the test, then we make an average of those values, and we subtract it from the measured value during the test, from the pressure created by the fan during the test. The problem is, well, we have no idea what is happening between the 2 periods we measure the zero flow pressure. It's not necessarily steady, and the wind can be very different during the test than before and after the test. So this is the first issue. The second issue comes with the external pressure measurements. According to our ISO standards, we have to place the exterior pressure tape some distance away from the building, fit it with a T-pipe. I forgot to draw it, but we are supposed to put a T-pipe here. And it shall not be close to other obstacles. So theoretically, it shall be like that, with an external pressure that is absolute. In practice, it's usually very difficult to find a location for the pressure tape that won't be influenced by an obstacle and the wind on this obstacle. So what happens is that theoretically the calculation assumes that you measure that, so indoor minus an absolute external pressure. In practice, we measure that plus something with a pressure coefficient that depends on the obstacles. It can be the building itself, or it can be something else. So the delta P0 is ranged with the wind speed, the square of the wind speed. This wouldn't be an issue if the wind speed were constant, but as it is not, it's increased the impact of fluctuating wind. So to limit this impact, what your ASTM proposed is to suggest is to have a pressure tape on each face of the building and then average it with the manifold. It does actually reduce this impact as it averages CP coefficients of the various faces, so it's closer to 0. But it's not enough. You still have something that remains here that theoretically should not be here according to the calculation. The other problem is the wind fluctuation. You see on this recording from Martin Prignon that during the measurement period, the zero flow pressure has varied between -10 and +10 Pascal within a few minutes. And it's induced large uncertainty because you cannot at all control those fluctuations and you cannot anticipate them. And even in a perfect world where we would have no wind fluctuation, perfect steady wind from the beginning till the end, and perfect. What is the problem is that the problem is not linear. It means that the N coefficient here, the flow rate coefficient, is not equal to 1. It's equal to 0.65. So within the equations, it does not simplify because the indoor pressure here is not the pressure at leakages. It's the result of the wind inside the building. It's very different from the pressure that every leakage in the building see. In fact, it's kind of an average of those 2 pressures, but with ponderation coefficients that depend on the size and on the pressure coefficient on each facade, the size of leakage and pressure coefficient. So the impact is when you do the test and you have wind like that, you underestimated this leak in pressurization, overestimated it in depressurization, and for this one it is the opposite. And the correction with delta P0 is not enough to overcome this. And so those are calculations of the error that we have made. And we see that usually if the whole building is pressurized or depressurized, averaging the results really helps to reduce the error. But we see that in some cases, for some very specific leakage distributions, we do still have an error. So to sum up, there is 4 main wind issues: wind variations, pressure measurement locations, wind fluctuations, and model error. And I guess you have had a lot of time to think of your questions, so I will be now happy to answer it.
It looks like people are afraid.
Yeah.
I have one question. Like, where did the 5 PA come from?
You don't have this in the ASTM, or do you have the same or not?
I don't believe so, not an ASTM. There, in other standards, there is USACE would be a common one over here that has a maximum allowed bias pressure.
In fact, yeah, it's in the ISO standard in 9972. What's the well, this is a limit to limit the uncertainty. I have no idea how they choose 5 Pascal at the beginning. Well, it happened to be quite effective to limit effectively the uncertainty, but we found out that in some cases we could have, depending on the leakage repartition in the building, we can have not that big uncertainty while having a pressure above 5 Pascal. But in fact, I have no idea where it comes from at first, but this is a very strong limit in the ISO.
And then, go ahead. Do you think if you could measure the winds, the effect, or do you think during the test, if you could measure the wind speed at the same time, then that would minimize the impact? Like if you said somehow, like not just before, not just after, but during the test, if you through software, you could measure the wind at the same time?
Yeah, I think that would be good to be able to measure the wind during all the periods and to see if it looks like the same at the beginning when we have the delta P0, during the test, and at the end when we do the other zero flow pressure measurement. That would be great to do that. But the issue is, where do we put the sensor for the wind? Because it's not that easy to measure wind fluctuations, in fact. You'd never know how, well, shall it be at the top of the building? Shall it be on the wall? Shall it be a few meters away? When you are in a city, it's not that easy to choose the right location for the wind sensor.
Yeah, that was going to be my next question. But
so, well, yeah. In fact, measuring the impact of wind on the building with the pressure, the way the indoor pressure change, is more interesting. But of course, you cannot do that during the test. So maybe we could measure the impact of wind on a small box outside the building or something that would reproduce the impact of wind inside the building. I don't know. Maybe we could measure pressure change in something outside the building to see if we see big fluctuation like that.
Yeah, Lee, you got a quick question?
Yeah, the 5 Pascal limit, is that, so that's stack and wind? So if there are gusts of wind that take it over 5 Pascal, does that mean that you are not able to test that day and you have to come back?
No, we do an average. In fact, the 5 Pascal is, I've got the text here of the standard over there. The 5 Pascal is, we do an average of all positive value before, all negative value before, then another average of all positive value after, and then another average of all negative value after, and we check that those four average here are below 5 Pascal. So if there is just one gust, it's okay. But if the average of positive value or the average of negative value is above 5 Pascal, then you have to come back later to do the test.
Okay. 2 more questions. That interval that you're recording the average, is that changeable or is it a set interval for the beginning and the end pressure averages?
You mean the length of time you have to record it? Yeah, well, it's minimum 30 seconds, but it shall be more, much more than that. But I will not spoil the end of my my presentation because it will come at the end. Yes, okay. We should do much more than 30 seconds. Let's not spoil him.
There was a question from Dan. How much wind in mile per hour does it take to really influence a test negatively? So like how strong of a gust would it take to really cause negative impact on a test?
Well, what the standard says, the ISO standard say, I'm sorry, I'm not speaking in miles per hour, but the standard says
okay.
6 meters per second. And what does it make? It's miles per hour. Is it 4 miles per hour? No, that doesn't work. 6 meters per second. I leave you to translation. Say that it's highly improbable that above 6 meters per second of wind, you will succeed in having a less than 5 Pascal different pressure in your house. And it's true. We have shown with the calculation that indeed it's only for some very specific leakage repartitions, and you can have more than 6 meters per second of wind and have less than 5 Pascal.
Okay.
So I don't know if you have made a translation between 6 meters per second and mine.
Our software takes it in meters per second anyway, so that's great.
Someone entered in the chat too. It's about 13.5 miles per hour.
13, okay.
Yeah, it's about 13.
Okay, so I just multiply by 2. Okay, very good. Easy.
Okay, I think that is all the questions we have from the audience.
Okay, so maybe. So let's do the literature review now. Yeah. So I hope I will not lose the sound again. So let's try it. There are, as I said at the beginning, there's a lot of people that are working on this subject, and in fact, everybody has his own approach to study the impact of wind on airtightness test. Some people do much prefer to remain behind their computer and do some simulation and test thousands of things and to test the impact of wind, and that's the part of the simulations persons, and I'm one of them, so I cannot say nothing about that. Some other people agree to go up to the end of the corridor in their laboratory and perform measurements on a smaller scale. And some other people do definitely prefer on-site measurements and perform blue order tests on-site to test the impact of wind on airtightness tests. All those three approaches are very different, but are very complementary one from another, have not the same benefit and drawback, and I will just give you a short review of what has been done until now. So we will start with the simulations. What's very good with the simulations is that it's possible to control all inputs and study impact independently. If you want a constant wind of 6 meters per second exactly during all the tests, you can do it with the computer. It's very easy. The other very good thing with simulation is that it's easy to test thousands of configurations, leakage repartitions, wind speed, wind direction, etc. Thousands of configurations, and to generate the results, you just program the simulation on your computer, come back the next morning, and thousands of tests have been done during the night, and this is quite good. The main drawback is that wind and buildings models cannot be exactly realistic. You cannot exactly model a real wind. You cannot exactly model real cracks in a building, the real repartition of leakage. So you have a lot of hypotheses. You have to test a lot of things to see what hypotheses matter and what not. And it won't, in any case, take into account all impacts that wind can have on the result of an airtightness test. The findings in the literature, in fact, there are two sorts of simulations. First, a steady wind has been simulated by Rémi Carrier and myself 3 years ago on a 2 leaks building. Yeah, we found out, and those 2 leaks, what we were doing is that we were putting them bigger and or smaller on each side to see the impact of the leakage repartition, leakage distribution, and we see that the error due to steady wind depends really much on leakage distribution and is mostly critical for single-sided building. So the impact of wind is worse when you are testing only, for example, only a dwelling in a multifamily building, what we do a lot in France. At 50 Pascal, the impact of wind is within 12% up to 10 meters per second. So this must be 20 miles per hour or so. And at 10 Pascal, the error can reach 60% for wind speed up to 10 meters per second. So at 50 Pascal, it's not that much, really. You have very high wind and it's not much big error. But when you perform the test at 10 Pascal, then it can be very important. And again, it's very sensitive to leakage distribution. So this is the maximum for a given distribution, not the value for all buildings. And we have also compared those results with other sources of uncertainty, such as measurement devices and regression methods and so on. And we found out that at 50 Pascal, the uncertainty to wind up to 6 meters per second remains smaller compared to other sources of uncertainty. So this is the 13 miles per hour. And for an indicator at 4 Pascal, the impact of wind is dominant at 4 meters per second. So according to the indicator you use, if it's at 50 Pascal or at 4 Pascal, or even bigger maybe, you shouldn't have the same limits for the wind speed to perform the test. Rémi Carrier, that does not have enough with the steady wind, has also simulated unsteady wind with some isothermal models and quasi-steady compressible models. He found, of course, much larger uncertainties than the average wind alone, but what is important is that the frequency of the gust has a very significant impact. And it has been confirmed by Dimitrios Kraniotis. He has shown that even with CFD simulations, he had a constant an average width of 5 meters per second, and he put gust, high frequency gust and low frequency gust, and found out that high frequency gusts were creating 100% more air change per hour than low frequency gusts. And that gusts creates a pressure difference around 50 Pascal, which is quite used when you're talking about an air tightness test, because it's basically the value of the maximum of the test. So what is needed to perform more simulations? First of all, we would need simulations that include the stack effect to see the interaction between wind and stacked, because it's really unknown for now. We will need to simulate multi-zone buildings, for example, the impact of a crawl space or other dwelling around the tested units in a multifamily building. And we will basically need a better characterization of unsteady wind and the response of the leakage to the gust to know till which frequency it is important to see the impact of wind, because probably as the cracks will act as a buffer, the building may not react exactly the same way to very, very high frequency to just high frequency or low frequency gusts. So there is a need to better characterize wind and the reaction of the building on those frequencies. So the second step, the second way of estimating the impact of wind is to do laboratory testing. So you have here an example of a wind tunnel that Adeline Melois set up in Antipeur in France. So this is a big fan, and inside she has a mini building that she turned around and changed the wind to estimate the impact. And this is his air tightness test device here. What is good is that it's very good to check the accuracy of the model. So you can make a model, check it on a wind tunnel, and then go on with some more tests in the model. It's also possible to control wind speed and wind direction, so it's all parametric studies. This is good. But the difficulty is there are various difficulties. One is it's very difficult to be representative with a reduced scale, because you have issue with Reynolds number, leakage behavior, and the gusts do not react the same way, so it's quite difficult. And it's also difficult to represent the wind spectrum of natural wind with a fan. Try to do some gusts with a fan like that, high frequency gust, it's not that easy, you have too much inertia. And it's also very difficult to study the interaction with the stack effect, of course, because as you are on reduced scale, you have to use very bigger temperature difference, which is not easy to do. So the results from Adeline have not been published yet. The only study we have in laboratory were the ones performed in Nottingham by Xiao Feng. And well, what he has done, he has put a very big fan on a test cell that he had outside to performed the test, and they found out that high spin wind in one direction induces 16 to 24% lower results for an indicator at 4 Pascal, and the winds become mostly insignificant under 3.5 meter per second. And another finding that we have about wind tunnels, a study that has been done in the purpose of calculating CP coefficients of building, of facades. Jafari and all has noted that it was almost impossible to test, to achieve similarity of the turbulence for low-rise building. You can do it for high-rise building in a wind tunnel, but for low-rise building, it's very difficult to reproduce the turbulence spectra of the wind in a wind tunnel. So this is a big limit for laboratory testing. So what is needed to continue with laboratory testing? To define the wind that shall be modeled, first of all, is it the peak of intensity or the high frequency, and to model the environment, and also to model the environment, because the wind tunnel usually represents only one isolated building, and you may want to see what is happening if you have trees or other building around, and it's not that easy to do it in a wind tunnel. You have to have a much bigger wind tunnel. So the last point is, the last possibility is to do on-site measurement of the impact of wind. So the big benefit is that it's more than realistic. You have no model assumption, you have a real wind, real building, real leakage. That's wonderful. And you can use those results also to validate model scale results. The main drawback is that it is difficult or maybe impossible to do parametric studies. You cannot control the wind, you can control the leakage distribution, but it's difficult to keep it realistic. And well, it's very time consuming to perform hundreds and hundreds of tests, and it can be, of course, as time consuming, very expensive. But still, it has been done, and Ian Walker from the University of California has done a really great study with 6,000 tests in 6 houses with various wind, various leakage, level, and distribution. He found out that below 3 meters per second, it's recommended to perform a multiple testing if you want an indicator at 4 Pascal. But above 6 meters per second, a single point testing at 50 Pascal and an extrapolation to 4 Pascal is recommended. And and also that averaging pressurization and depressurization tests reduce the uncertainty by about 12%. So it's very important to average pressurization and depressurization tests. There is another field study in the literature performed by Stephanie Wolfmeyer and Paul Simons. In fact, they came to measure a very high building, and when they came on site, everything was prepared. There were a lot of wind, and they say, okay, shall we leave now or do we perform the test? So they performed the test, and then they came back the day after, which was much less windy, and performed another test to compare the results, and found out that by averaging the results between pressurization and depressurization, it was very reproducible with less than 1% difference, and that the impact of wind was also reduced by averaging the measure value of 3 test points located on 3 different sides of the building, because they were not able to place the external gauge somewhere that were not influenced by the wind. So what is needed? More study would be very good to be able to draw general conclusions. The study of Yen is wonderful, but I mean, it's on 6 houses located in some places. We will need to see what happened where in places where the wind is different and the gust may be different, and also on other construction habits, because we do not build the whole house the same way in Europe as you do in the US. And we will need to control also some parameter, to do some parametric studies, but keep them realistic, so not to have too large opening, because if you try to make openings, then you make something that is not realistic in the building. So I guess you still hear me, right?
Yes, we can.
Good. So do you have any question? I will switch on the light because it's almost night here.
Yeah, I think this really echoes some of the issues that we've been seeing here in the U.S. For testing residential buildings, multi-point tests are pretty much still brand new here. And so ResNet, so where we have our MERS raters that do a lot of new construction, the standard recently changed where if you don't do a multi-point test, you have to add 10% to your single point leakage. So that's really encouraging these raters to do a lot of multi-point tests. And we're noticing when they get to those lower pressures to 20, 10 pascals, wind can really screw them up on the test because it'll time out or they won't be able to collect their data. So it's definitely become more of a discussion. And yeah, everything you talked about here for those low end pressures is exactly what we're seeing in the field. So.
And what is your pressure indicator? What do you use as a reference for the air tightness? Is it N50, Q50, or is it equivalent leakage at 4 pascal? What is it?
50 pascals. Or they'll do the ACH, the air changes per hour. So either of those two metrics are accepted. So just the cubic feet per minute at 50 pascals or the air changes per hour at 50 pascals. And on those standards, it's just required that the reference tube be at least 5 feet away from the fan. So that's usually how they're tested.
5 feet away, okay. And yeah, well, in my view, but again, I won't spoil the end of my presentation. In my view, if your reference is at 50 pascal, there is absolutely no point in making a multiple test point. It's good to do it in pressurization, depressurization, but in my view, there is no reason to have a point at 10 pascal and do a linear regression that will bring another sources of lot of uncertainty itself. But yeah, we are doing also only multiple tests, and ISO 9972 only allow to do multiple tests. There was no possibility to do single point test, but I cannot really see why it is this way. It's useful to test that if you have something that open in the building while you are doing the test, you see that your slope is not straight because, for example, something has broken or something. But you can still do that without using the point to obtain the indicator at the end. That's my view.
You're suggesting more of like a 1-point test at 50 pascal, and then would you repeat that point multiple times to make sure you get roughly the same answer?
Yeah, we'll keep it like 10 minutes.
Okay. I think that the single
and I will do minus 50 and plus 50. This is very important, not only 50.
Okay.
See, that's another
Again,
thing. Here in the U.S. for residential, we only test in one direction. So
yeah,
it's usually depressurization. So yeah.
And not required to do multiple points for that one test target. So it could be influenced by wind, which is probably why they do the 10% penalty.
Yeah. Thanks, Valerie. That was interesting to hear your take on that. So.
Yeah.
I will comment to it in the last part of the presentation.
Real quick, one question. You mentioned the leakage repartition. Is that just referring to the leakage distribution in the building?
Distribution,
how many leaks
sorry.
And where they're located?
This is a French word. We say repartition in French. I mean, when I said repartition, I mean distribution all the time. I try to correct myself, but it's come back.
No, that's okay.
After holidays. Sorry. Repartition means distribution in my mouth.
Okay.
Shall I move on, or is there
other
questions?
To be sure, Dan Aaron has another question for us at some point.
Okay, so let me check this. There. So now the last part of the presentation is how shall we minimize the wind impact on air tightness test results. So we have spoken at the beginning about the zero flow pressure difference and above those 5 pascal. As I said, it's, you have this zero flow pressure difference is important, but the subtraction is not enough to cancel the effect of wind. It's useful to minimize the wind effect. It's useful to avoid tests in case of strong wind and stack effects, but it's not enough to cancel the effect of wind. The recommendation would be, if you are doing a test in a windy condition, to increase the duration, the frequency of the measurement. Parmentier et al. Has said that the duration of the record should be defined by a spectral analysis of the wind, but of course you cannot do that for each test. I mean, spectral analysis of the wind is kind of complicated things to do. But he recommended an acquisition frequency between 10 and 40 samples per second, while actually we just do 1 sample per second according to the standard. And Twinio and al. Have found out that if you increase the measurement period of the zero flow pressure difference up to 60 seconds on medium winds day and 90 seconds on high winds days, you can reduce the uncertainty by 9%, which is very huge. And also, what would be interesting is to record fluctuations. As we were saying, the standard in the ISO standards only calculate the average of the delta P0, but it would be interesting to calculate the standard deviation also of the zero flow pressure and give a zero value that shall not be overpassed. And also to monitor the wind during the entire test to detect variation, as we said, but the main problem is where do we put the sensor to monitor the wind, and how do we do that, which kind of device. Another issue is the location of pressure tapes. The location of the external pressure probe is of importance, since the external pressure is used as a reference for every relative internal pressure measurement, including the zero flow pressure. What is fundamental is not to move the gauge during the test, to leave the pressure probe exactly at the same location before, after, and during the test, so during the whole test. And other important things is, yes, to use a T-piece at the end and put the pipe some distance away of the building, somewhere that it's not influenced by the wind and obstacles. And if it's impossible, then the good advice is to average pressure taken on at least 3 facades. But in my view, when possible, the first thing to do is to put the pipe some distance away. And Yuri Novak is in the last study has tried that. He has put 4 external pipes at 5 to 8 meters from the facade of a house. He has performed 9 tests, and for each test got 5 Q50, so 1 for each pipe and 1 for the average. And he has seen no impact of the location of the tape on the results, because it was far enough and using T-piece. While Modera and Wilson in 1990s have shown that they were not able to put the external pressure tape far away enough, and they have found a slight negative bias with increasing wave speed, and that using 4 pressure tapes averages gave less bias than with just 1 pressure tape. The regression model also is a big issue. I don't know what you use in the ASTM, I'm not sure, but the ISO 9972 requires to use the least square methods and to derive the C and N coefficient from the experimental measure. Without further precision, what most people do, what everybody do, I would say, is to use the ordinary least square method. But according to Delmott in a study of 2013, the ordinary least square method, so this is the basic linear regression, I would say. It's not applicable here because you have both an uncertainty on pressure and an uncertainty on flow rate, and you cannot use the OLS if you have an uncertainty on the pressure on the x-axis. And also, you cannot use it if you have uncertainty that varies on the flow rate measurement from one point to another. That's why the Canadian standards and the German standards recommend to use the weighted least square methods to limit the influence of low pressure points and have the smallest quadratic deviation for the actual measurement point. In fact, there are other options that exist, weighting by residual method and weighting by measurement uncertainty method. Well, both of them work equally well and better than an ordinary least square method for low and high pressure, according to Martin Trignon. And then there is a question we are talking about. Shall we do only 1 point measurements, but a longer point and around 50 Pascal if we have an indicator at 50 Pascal, of course? Well, the benefit of that is that you have a good precision on the measurement, especially in windy conditions. You have low standard deviation. You calculated the leakage is not influenced by the error on the low pressure point and on the regression error. It's much easier to implement a 1 point measurement than a complex regression and the calculation of a discrepancy ratio to minimize the impact of winds. I mean, it's much easier just to do 1 point. And the test would be quicker with lower risk of wind variation, and it would also increase the possibility to perform both pressurization and depressurization tests. I mean, as far as you just 1 point to do, it's much faster. And it would allow longer duration of pressure measurements. And in case of wind, maybe you can go up to 10 minutes and see how it varies or something like that to see, to calculate the uncertainty of your measurement, really. The main drawback is that it's not relevant if you want to estimate the infiltration rate in your building under natural conditions. So if you want to have an indicator at low pressure, for example, between 1 and 10 Pascal, I mean, because there is two reasons. The artificially induced high pressure during the test may slightly deform the airtightness defects, and also you would need to use a theoretical fixed N value to extrapolate the flow rate at a lower pressure, and it would induce a large error. So according to Ian Walker, he has looked at his database and found that well, the average is around 0.65 for the N value, the flow rate coefficient, but with a standard deviation of 0.057. And a change in 0.1 in the measurement, so if you move it to 0.55 or 0.75, could induce an error of 29% by extrapolating from 50 Pascal to 4 Pascal. So if your indicator is at 50 Pascal, in my view, I see no reasons to do a multi-point test. But if you have an indicator, if you want to have the flow rate at a lower pressure, then it's important to go as close as possible to this low pressure. So we should adapt the pressure difference sequences also in case of wind to minimize the impact. Average the result of pressurization and depressurization test. Estimate a flow rate at 50 Pascal and perform a single test point. So if you want to estimate the flow rate at 50 Pascal, you perform a single test point. And if you want to perform a flow rate at to estimate the flow rate at 4 Pascal, you do multiple test points up to 5 meters per second, and above 5 meters per second, a single test point at 50 Pascal and extrapolate. And what is important also is to carry out similar pressure measurement during the air tightness test and during the zero flow pressure measurement in terms of duration and frequency to be consistent, and use an average of the same number of value over the same time interval. So to sum up, to minimize the impact of wind, you have to improve your zero flow pressure measurement. You have to choose carefully the location of pressure taps. You have to use a weighted method for the regression instead of the ordinary least square method, and adapt the pressure difference sequences to what you want and what you have in terms of wind. And there I am. Do you have any questions?
No, that's perfect, Valerie. Appreciate it. You know, one thing with when you recommend maybe taking the measurement for 10 minutes, that would just be like if it was a really windy day, like if it was greater than 6 meters per second, then that's the day that you would do the 10-minute test. Yeah,
I mean, 10 minutes, yeah, it's a very, very windy day. 10 minutes is what is stated you will have, I mean, all the wind variation you will capture in 10 minutes, but that's extreme. I mean, you don't necessarily need that. But if you see huge variation and you see that it's impossible to stabilize your test, then it may be useful to take more data, to have more data for the average to limit the uncertainty. But it's definitely not something you will do all the time. It's something for windy and gust days, yeah.
And I suspect that in that situation, then maybe somebody has their gauge on like a 60-second time averaging, and they just take they record the reading every minute for 10 minutes and then average those results together to come up with the final number.
You mean average the average? That's what you mean?
Yeah, I'd like to
10 times 1 minute?
Yeah, 1 minute average on the gauge and take 10 readings off of it and average those.
An average?
Yeah.
Yeah.
Like
yeah, that works. Yeah, as long as yes, if you want to calculate the uncertainties, then you will need theoretically, you need to have each point measurement to have a good calculation of the uncertainty, because you will want the standard deviation. But if you just want one value without the uncertainties, then you don't need all the information.
Yeah. And then what about the difference between mechanical dampening and like averaging through software? Like, see, some people will take their reference tube and put it in a beer can here to try to minimize the velocity of the wind hitting the reference tube. Like, have you ever looked at anything like the mechanical aspect of trying to dampen the wind versus like through software with like the time averaging we talked about in the gauge?
I think the two things are complementary. In fact, the standard says that ISO standard says that you can either put a T at the end or put it in how they call it, a perforated box, the external pressure, to avoid the effect of the wind. But those are two different things. Put the gauge in the perforated box is made to avoid this issue here of having a CP coefficient, and taking multiple test points is made to limit the impact of wind fluctuation. Well, to calculate, to limit the impact of wind fluctuation. So those are two different objectives that are complementary.
Yeah, I see.
Yeah, so that would be like similar to what a lot of people are doing. It's not really a perforated box, but they'll take it and put it in the tip, put the tip in the case that the manometer comes in, just to try to keep wind off it that way. That's usually what we see, just to try to see people get around that.
Sorry, I didn't get it. In what do you put the gauge?
Yeah. People take the end of the reference tube outside and put it in the manometer case. For us, it's the red case that the manometer comes in. So they'll just put the end of the tube in that and set it outside, and just to try to keep the wind off of it that way. But that's probably the most common way that I see people trying to keep wind off of the.
The pressure tap. Yeah, they put the pressure tap in a box or in a.
But is it an open box with a lot of hole, or is it a closed box?
Yeah, it's like
a cloth case.
Yeah.
So it's perforated.
If there is a lot of perforation, then it's good. But if it's almost closed, then it is not good, because you have the impact of the wind on the closed box also. Because if you have just some leakages, you would have also a pressure difference between inside your box and outside. So it needs to be well perforated to work.
What do you think is better, using that method and trying to put the end of the tube in a perforated box, or putting a T on the end and running a line to opposite sides of the building to get an average across the building? I know that was mentioned.
We always put a T at the end in France. I have never seen anybody use the perforated box, but I guess if it's in the standard, that means that some people do that. Well, the T work well if you are able to know where the winds come from and do not put one of the end of the T straight in the wind direction. The T works quite well. So, yeah, I mean, okay. But I guess if.
And the T helps prevent like the velocity of the wind like being pushed into the tube versus just measuring the pressure.
Yeah, you measure just the static pressure and you avoid having the dynamic pressure.
Yeah.
We had an audience question. Is there anywhere in the standards that allows averaging of depressurization and pressurization results?
Oh, yeah, it's allowed. It's even recommended, but it's not mandatory. Yeah, it's definitely allowed. And in some countries, such as Belgium, in their own, because, well, the ISO standard, the way it works is that every country use the standards, but make a national annex to do some, let's say, adjustment that is adapted to their construction habits and so on, because we are Europe for everything, but not for ventilation and pressurization. So we have all our own habits. And so, yeah, in Belgium, for example, in their national standards, they impose to have depressurization and pressurization, an average of both. If they don't do that, they have a penalty, but it's huge. It's something like 20%, I think.
Wow.
Okay.
If they cannot do the test in both way. But in the ISO, it's just recommended.
Okay.
Yeah, here in the States, we do that for most commercial standards. For like big commercial buildings, we'll test in both directions. But yeah, our residential standards just aren't that involved quite yet. So maybe they will be later on. But I think taking the going from single point to multi-point was maybe a step in that direction. But I'm not sure. It'll be interesting to see what happens later.
To do even more points. Then if you have multi-point and you do it in both ways, so you double once again. Yeah. But the problem in residential building, I don't know how it is in US, but I think you have a lot of cooking hood, right?
Yeah.
And sometimes it doesn't close. So when you pressurize the buildings, the flap, how you call it, open.
The damper. Yeah, and
so
that's why we do just mainly depressurization for our residential here. Yeah, because we have the kitchen hood and then we have bath fan exhaust going to the outside as well. So if we do a depressurization test, we usually get a tighter number that way.
Yeah, and yeah, that's an issue. But yeah, you have to deal with that. Either the penalty of 20% is less worse than the flap opening. So
right.
I mean, in Belgium they do both way. And now, at least in France, we have almost much less cooker hoods than we used to be because of the mandatory airtightness test and the objective value. If you have a cooker hood, it's very hard to achieve all the rest of the building should be perfectly airtight. So we have much less than we used to have.
Right. Did we have any more questions trickling in there, Lee, or was
I think that was our last question, unless anyone else in the audience has something.
Just one audience comment about this was excellent. And I agree, Valerie. I really appreciate you taking the time. I know it was your holiday when you put this presentation together. A lot of great information. I know it's late there now, and really appreciate you kind of hanging in there and doing this with us.
Absolutely. Yeah, this was great.
Thank you.
Thank you.
Hi, and thank you for inviting me.
And we can overcome technical challenges such as.
I'm very sorry for that. I don't know what happened.
It all worked out.
Yeah. Well, to everyone listening, we are recording this. So if there's anyone with your company or a colleague that you would like to see this, we'll have it up on our YouTube channel later on this week. And if nothing else, Valerie, thank you so much again.
Yeah, thank you.
Thank you.
Joy, have a good day. Bye, everyone.
So bye. Have a good night for me now. It's 9 o'clock. But have a good day.
Bye now.
Bye-bye.
Yep.